Howdy. I'd like to take just a few minutes to talk to you about potential energy graphs. They are some of my favorite graphs because they give us so much useful information. Let's consider the potential energy function for some random object. And I'm going to make up a potential energy function here. We'll take this one just because it looks kind of cute. And what I'd like to do is to consider the information that we can get from this graph right here. First of all, the potential energy is going to be measured in joules, so maybe this is like 5 joules here, and maybe this is x equals 10 centimeters up here. Well, let's make it 10 meters just so we don't have any unit issues. And so, of course, this would be at x equals negative 10. The first thing that we can read off of our potential energy graphs are the changes in potential energy when an object moves from one location to another. So, for example, let's say that the object moves from x equals negative 10 to x equals 0, and we want to know how much potential energy does the object lose. Well, that's a simple matter of reading delta U right off the graph. I can go to the 2 points in question at x equals 0 and x equals negative 10, and I can compute the delta U here as the change in energy, being careful to do final minus initial. So final is 0 here, initial is 5 there. And so I get a negative 5 joule change in potential energy. But wait, there's more, because since delta U is also equal to the opposite of the work done by the force, and therefore also equal to the opposite of the kinetic energy imparted by that force, I can say that when the object travels from x equals negative 10 to x equals 0, I can immediately say that the object is going to pick up 5 joules of kinetic energy along the way. So I could actually compute the speed of the particle at this point, assuming I knew the particle's initial speed. And that's really nice. So potential energy graphs are useful because I can use them together with work energy to compute kinetic energies and changes in potential energies. But there's more. Because potential energy is defined as the integral of f dx, and to make this definite, let's integrate from the 0 point out to some point as x. And we remember to take the opposite of that because the potential energy is the opposite of the work done. Therefore, it follows that when I take the derivative with respect to x on both sides using the fundamental theorem, what I get is that du dx is equal to the opposite of the force that the particle experiences. Or another way of putting it is, the force that a particle experiences is the opposite of the slope of the potential energy curve. Now here's what this means. Go to any point along the curve. Let's say I go to x equals negative 3 right here. Find the slope of that curve by drawing a tangent line and computing its slope. And it looks to me like the slope of this tangent line is about 2.5 over and 2 up. So the slope du dx is equal to approximately 2 over 2.5, which is going to be about 0.8. And that would be joules per meter. Or 0.8 kilogram meters per second squared. What does this mean? This means that the object sitting right here is going to experience a force as a result of this slope of kinetic energy, pushing it in the opposite direction, so that since my du dx is equal to positive 0.8, my force is going to be negative 0.8 kilogram meters per second squared. Or go to a second point right here at x equals about 3. Draw yourself a tangent line. And it looks like the tangent line here has a slope of about negative 2/3. We'll call it negative 0.7. This means that the force that the particle experiences is going to be equal to positive 0.7 newtons, the force pushing it in a positive direction. You may have noticed that whenever the object has whenever the potential energy graph has a positive slope, the object will experience a negative force, and vice versa. And so one very convenient way of thinking about these potential energy graphs is that the object literally rolls down, and as it rolls down here, it's going to experience a force pushing it this way. And then once it gets to here, it'll experience a force pushing it back the other way, so it will lose speed until it hits its a speed of 0. And it'll come back here, and so on, and so on, and so forth. In other words, we can think of these potential energy graphs as almost like representing a sort of roller coaster shape that the object will travel along under the influence of gravity. And mathematically, that's not so far off. So we can do two things so far with our potential energy graphs. One is to measure changes in potential energy, which also give us changes in kinetic energy. And the other is, through the derivative, or the slope, to find the force exerted on the particle at a particular point. Now, from calculus, you already know that it's very special when our force or our slope is equal to 0. And the points on the graph where our slope is equal to 0 are going to be places where we say that the object is in equilibrium. Why? Because the force on that object is equal to 0. So the locations of 0 slope on the UX graph are points of equilibrium. We can actually classify these points of equilibrium a little bit according to their behavior. If you take a look at my object that is rolling around right here, if I were to displace the object from its point of equilibrium up here, we now experience a force pushing it in this direction, back towards the point of equilibrium. But if I were to displace it over here, it would experience a force pushing it in the positive direction, back towards the point of equilibrium. In other words, no matter which way the object moves, it's going to experience a force that pushes it back towards this equilibrium point. And so for that reason, equilibrium points that are concave up, we call stable equilibrium points, because a slight displacement from equilibrium simply sends the object back towards its equilibrium point. By contrast, imagine that your object is up here at the top of this hill. Let's get some of our slopes out of the way so that they are cluttered in the picture. If it's up on top of this hill and it is displaced ever so slightly in either direction, then it will experience a force sending it away from the point of equilibrium. If it's here and it's displaced ever so slightly here, it will experience a force sending it away from its point of equilibrium. So this point of equilibrium right here at x equals 2, which is concave down, is called an unstable equilibrium point, because any slight displacement sends it shooting off away from its equilibrium point. And if you think about the fact that an object at the atomic level can never be perfectly still, what that means is that an object at an unstable equilibrium point will never stay there. Finally, you notice that we have an interesting situation over here where the entire curve appears to be flat. And here, if I were to displace my object a little bit, it would experience no force at all. And we call such flat equilibrium points neutral. Now, how can I characterize these mathematically? I characterize them in terms of concave up, or concave down, or flat. If we were to characterize them mathematically, we would say that the second derivative of the equilibrium, of the potential energy, is positive. The second derivative of the potential energy is negative. or the second derivative of the potential energy is 0. This quantity, the second derivative, is what measures the concavity. And we call objects with we call curves with positive second derivative concave up here, ones with negative second derivative concave down, and ones with 0 second derivative concave neutral.